Hello, every parts of the world. Okay, welcome to my YT world. Welcome to my YT channel. Okay, class. Okay, this is another topic. This is a foundation to nuclear chemistry. Actually, I already live streamed last night, but it was very sad. I have a very weak connection. Okay, and I was interrupted several times. Then it was, I think, a little bit longer, but the final uploaded video turned out to be shortened, and it was only 6 minutes, despite of the fact that it was done more than 30 minutes. Okay, due to the interruptions of the of the connection. Okay, network provider weak signal connection, something like that. So I have to repeat, and I want to make this clear because this is very, very important in the understanding and in the learning of nuclear chemistry. So we need to go back to the basic principles and basic theory, okay, regarding the atomic structure, right? So the first thing to discuss is all about atomic theory. So if we talk about atomic theory, what comes in our mind is John Dalton, okay, a scientist who discovered the atomic theory. And this is very specific. This is modern atomic theory. Okay, do not forget. Okay, don't forget the word modern. Okay, modern atomic theory. So this is all about all matter is composed of an atoms. Okay, so as we can recall, matter is composed of solid, liquid, and gas. Okay, and the definition of matter is anything uh, that occupies space and has mass or has weight. So meaning anything. So the anything in this world, okay, is a lot. It could be solid, it could be liquid, and it could be a gas. Nothing else, right? So if we speak about moisture, that is a gas or a vapor. Okay, steam is a vapor or a gas, something like that. So all substances in this world, in the planet Earth, are composed of solid, liquid, and gas. And this solid, liquid, and gas are composed of an atoms. And atoms composed of particles. Okay? So first, we need to define the atom. Okay. Atom is the smallest particle of an element, okay, in the nucleus. When I mean in the nucleus, it could be either inside or outside in the nucleus. The inside in the nucleus will be the neutrons and protons. Oh my gosh. And and the outside will be the electrons. Okay? Like that. Sorry for a while. I have to terminate the call because I do the vlogging and live streaming. Okay? Like that. Okay. Again, atoms are the smallest or tiny particles of an element. Okay? So, meaning to say, this is the defining structure of an element, and this is the basic unit of matter. Again, atom is the basic unit of matter and a defining structure of an element. Okay? For example, I may have hydrogen. Okay. Okay, hydrogen. I will show you to a clear understanding. Okay, I have to show you, right? So hydrogen like this. Okay. For example, hydrogen. So we have the nuclear charge or the charge of the nucleus of a hydrogen, okay, or the number of proton of a hydrogen is positive 1. Okay, here, the downside. This downside denotes the proton. Okay, or the atomic number. Okay, this one is the proton or the atomic number. Okay, and here is the mass number. Okay, so the mass number proton and the, okay, and this atomic number proton and the mass number, okay, these are all the defining structure of an element. Okay, and then the basic unit of matter, because element could either be a solid, liquid, or a gas. In this case, this is a gas, hydrogen. Okay, the basic unit of matter, and matter composed of solid, liquid, and a gas. And then gas, example of hydrogen. And these characteristics here or descriptions here are the defining structure of an element. So we can easily distinguish that this is hydrogen because this has a proton and atomic number of only 1, okay, and a mass number of 1. So we can easily say that hydrogen is the lightest element in the universe, okay, discovered by Henry Cavendish. Okay, through this descriptions, I may add another formula, which is mass number is equal to the mass of protons plus the mass of neutrons. Okay, so here it goes. Mass number is it in the top is equals to the mass of protons plus the mass of the neutrons. Okay, since mass of the again, since the mass of the hydrogen is 1, mass number is 1, let's substitute that here. Okay, I almost lost because I did not memorize that, So the mass number is 1 and the number of protons also is 1. So the number of protons is 1, automatically the atomic number is 1. But this is only for hydrogen, but okay, in the periodic table a lot of elements also, okay? Like that. Okay. So if you substitute the number of atomic number here, so it could be written as mass number is equals to the mass number of protons plus neutrons. So it will be equal to mass number is equals to atomic number, okay, minus the number of neutrons. Sorry, plus again, because it's only substituting the number of atomic number here. So mass number is equal to atomic number plus the mass of neutrons. Sorry. It's simple mathematics. Sometimes, even though how simple it is, then I get easily confused also. Okay. Like that. Okay, it's very important to, write carefully, okay, and memorized with better comprehension, okay, like that, something like that. So this is the hydrogen. Okay, now, so this will gonna be or equal to mass number is equals to atomic number plus mass of neutrons. This is gonna be mass number protons plus neutrons. Okay, this is gonna be mass number equals to atomic number plus neutrons. So here is another formula. Okay, since atomic number is equals to protons, so this will be the new formula. Okay, mass number will be denoted as capital M, small letter n, subscript. Okay, plus proton is only P, and the neutron is only N, and then you can substitute that to the equation. So you can solve already the what is being required for that particular atomic theory question, something like that. Okay, so that's it. And now we go to the discovery. Okay, in 1909, proton was discovered by Ernest Rutherford. Ernest Rutherford. So memorize this one, huh? So this will become your stock knowledge. Actually, I learned this in high school and also applied in the college. Okay. In year 1909, the protons were discovered by Ernest Rutherford. Then in 1932, the neutron discovered by James Chadwick. Like this. In 1932, the neutron discovered by James Chadwick. Okay. In 1897, the electrons was discovered by J.J. Thomson. Okay. In 1897, the electrons was discovered by J.J. Thomson. So it was the electrons were discovered first prior to protons and neutrons. Okay, you can see the gap of the number of years before the protons and neutrons being discovered. It took a lot of years, right? So, their scientific experimentation, okay, actual scientific experimentation, okay, with a series of, scientific research, of course. So, because scientific research is a basic foundation of discovery or any invention, right? So, it took a lot of years to discover, okay, in these three scientists. And now, since we are dealing with nuclear chemistry, I'll be able to specify also that the radioactivity is discovered by Henry Becquerel. Discovered by Henry Becquerel. I forgot the years, but I think it all started in 1850 to 1926. Okay. I'm not really sure for Henry Becquerel discovery, but I think it is 1850 to 1926 that Master Henry Becquerel discovered radioactivity. Okay. Okay. Radioactivity discovered by Henry Becquerel. Okay, the radioactivity meaning it involves radioactive substances chemical reaction that govern with the three emission reaction. Okay, the alpha ray or the alpha particle or the alpha emission, the beta emission, the beta decay, or the electron capture, and then we have the gamma ray. And the example for that is the X-ray. So those are undergoing the process of radioactivity. It's always governed with alpha, beta, and gamma rays, or let us say emission. When we speak about radioactivity, it talks about emission. Okay? So usually the questions will state like this. An element is bombarded to a neutron, okay, and then bombarded to an electron, something like that, to produce a product. The term is always like that, or alpha emission, beta decay, electron capture, something like that. Okay, so this is a radioactivity process. And then the X-rays is discovered by N. Roentgen. X-rays discovered by N. Roentgen. X-rays discovered by N. Roentgen. I forgot also the year. Okay. Like that. So these are the K scientists who played an important role in better understanding of the nuclear chemistry in relationship to the understanding of atomic theory. Atomic theory discovered by John Dalton, modern atomic theory. I don't have to put, just put that in your mind, something like that. And now I will show you the important data of these particles. These particles really, for example, if we have an atom, it's composed of particles that are mainly the electrons, neutrons, and protons, something like that. I'll show you. So if this is an atom composed of particles, proton, neutron, and electron. So, if this is an atom, this is composed of particles, the proton is positively charged particle. That's why it's positive. The neutron is electrically neutral. That's why zero, neutral. And then the electrons is electrically charged. Okay, electrically charged or negatively charged. That was negative. But the right term is really negatively charged, so it's negative. Okay, it's very clear. Proton, neutrons, and electrons. But there is the other one also, which we know as the positron. Okay, which is positive, like this. The other one will be positron, which is the positive electron. If we have the negative electron, we have also the positive electron, but this concept will not be used every time in chemistry. This is only exclusively in the nuclear chemistry topic or in the nuclear chemical reactions. Okay, it will never be applied in most cases to other topics in higher chemistry. All kinds of chemistry, right? For example, physical chemistry, qualitative chemistry, or in any chemical calculations, problem solving, okay, like that. Or in the redox, it doesn't involve positron because this is not widely used, okay, in other topics, and not widely used as a subject for the understanding of the majority, okay. But there is a theory known as positron, the positive electron, the opposite of the electron. Okay? Like that. Now we can write that one as in a brief manner. So the proton will be like this. Let's just always take hydrogen. Okay? Okay, and then we have the neutron, electron, positron, okay, this one, proton, 1, 1, mass number of 1, atomic number of 1, or the number of proton is 1. This H, or actually this is denoted as capital P, but we try to be specific to get hydrogen as an example. But actually the general formula will be 1, 1, P, capital P proton. Okay, but never mind, okay. This one is neutron, electrically neutral. So the mass number is 1. Okay, the atomic number is actually 0. But since this is a neutron, this is not an element, this is a general formula. Okay, so here the charge is 0 for neutron here. So meaning to say the bottom, okay, is the nuclear charge or the charge of the nucleus, then it is also equal to the number of proton. Then if you specify that as an element, that is an atomic number. Again, the lower part in the general formula, okay, for the neutron is the nuclear charge, okay, or the charge of the nucleus, which is 0. If we change this to an element, okay, for example, zinc, this will, the downside will become our atomic number and the number of proton. Okay, no issue already. Now, if we have the proton, neutron, you have the electron. So the electron will be like this, the mass number will be 0. Okay, the nuclear charge is -1. There's no other for electron. And the positron will be the opposite. We have denoted as small letter p to avoid confusion with the capital P, which is the proton. And thanks God we don't mention the capital P here because we use hydrogen as an example. So the small letter P is a positron. Okay, the mass number is 0. Okay, and the nuclear charge is, okay, +1. Okay, but if you go to the nuclear chemistry that undergo radioactivity process or nuclear reactions, there's a slight changes for the representation, okay, in the alpha emission, beta decay, electron capture, gamma ray, something like that. But it's the same principles using this basic knowledge. Okay, it's very clear. And now we go to the tabulation, including the mass. Okay, so in my research, in my reading, or a little bit of review, because it's been studied for a very long time, I think 25 years ago in my college years when I taught about best chemical engineering. Okay, since of course some retain in my brain and some are lost, so we have struck knowledge. Okay, the rotation is not very high already. So as far as I could recall, okay, especially numbers, dealing with numbers, usually you have to memorize, but the theoretical foundation or basic concept, it's already written in your brain, okay, because you understand it completely. If not completely, you understand majority of the, the principles, theories like that, okay. But for specific numbers, dealing with figures, for example, what is the value of this, certain atomic number like that, or mass number, or atomic weight like that, then you could not memorize all the time, except for common elements, non-metals, gases in the periodic table. Okay, something like that. So we have here proton, neutron. So we don't include positron, okay? Because this is not common used in the discussion of chemistry, only for a certain topic regarding atomic theory, or in the in the nuclear reactions or nuclear chemistry. That's why we are dealing with nuclear chemistry now. Okay. I just don't include the positron, huh? Okay, and then electron. Because the three basic particles are only proton, neutron, and electrons. So these are particles like this, and we have a charge like this. We have the mass number. Oh, Nasser. Morning. Okay.
Yes.
Yes.
Mia.
Yes. And then we have.
Mask. Go on.
EG.
I'm still on.
Yes. Coming, EG. Okay. This one. This is our atomic theory tabulation of data. The particles are proton, neutrons, and electrons. And then for the proton, our charge will be positive 1. For the neutron is 0. Electron is negative 1. Charges. Okay. Now take note, some textbooks are only using positive. So if positive for proton, that means positive 1. Or some textbooks also are using 1 only, that means positive 1. Okay? Because without putting charges either positive or negative, it's automatically positive. Okay, and then the electrons are negative 1. Some textbooks are using negative only. Don't be confused now. Okay. And then the mass number will be 1. Okay. And also the mass number of a neutron is also 1. No, 0. Sorry. An electron should be equals to mass number of 1. Okay. And then the mass for proton will be equal to 1.67 Okay. Like this. Okay. Mass number and the mass in terms of kilogram. Okay, proton. For the proton is 1.67 times 10 to the negative 7 kilogram. For the neutron, 9.11 or 9.109 times 10 to the negative. Oh, sorry. For the neutron is almost the same with the proton. For the mass, okay. So that means 1 is equals to nearly equal to 1. Sorry. And this is 0. Then mass number of electrons is equals to the number of protons. Not accounting the charge. Like this. It's correct, really. What made me confused is the mass number. Actually, the mass number and the term mass only, because the term mass is having unit, which is kilogram in this third column, right? And the mass number, based on what I understand, okay, the mass number of proton is 1, and equal also to the no, equal to the electron, which is 1, but the sign is not important anymore. So we can say the number of electrons is always equal to the number of protons, okay, but the sign or charges is not the important. Okay, like this. You will never consider the charges as long as it has the same number of electrons and the same number of protons. Number, Okay, I'm not talking for the value but the number. Okay, so there are two electrons in equal to two protons, something like that. So the number of electrons is equal to the number of protons. Okay, this is true because these protons and neutrons are, interacted each other in the center of the nucleus, they bind together, something like that, and the electrons are outside in the shell of that nucleus or an atom, in the outermost shell. That's the electrons. So in the inner shell of a nucleus is the protons and neutrons. So that's why they have a very strong nuclear reactions or nuclear force with each other. Okay, because their forces and reactions are going towards the center of the nucleus. Okay, something like that. Okay, it's gonna be like this and like this. So in this principle, sorry, the number of electrons is equal to the number of protons. So we have this principle in atomic theory, okay, that the proton and the neutrons are really partnered with each other, reactive with each other, or bind together, something like that. Okay, and then the nuclear reaction or the nuclear force are very strong. Okay, that's why it is being put inward, meaning in the inside of the nucleus. Okay, the nuclear force and the nuclear reactions are going closer inside the nucleus like this, proton, neutron inside the nucleus, and then the electron will be on the outside, the electron like this. That's why the arrow is uh, going away, meaning weak or less nuclear reaction or weak or less uh, nuclear force. That's why it is outward from the nucleus. This one, the nuclear force of proton and neutron, okay, is inward to the nucleus or pulling them to inside the nucleus, and then the electron will be the nuclear force and nuclear reaction is outward, pulling them away from the nucleus, something like that. Okay, so it's understood that the electron is lighter compared to this proton and neutron, of course, because this is negatively charged particle. Okay, negative, when we mean of negative, that is light, right? It's not having the mass, something like that, by common sense. That's why it's always on the outermost shell rotating this electron. Okay, in the outer shell of the nucleus, this negatively charged particle electrons are rotating because the nuclear force or the nuclear reactions are very less and very weak. So that's the situation. And the proton and neutron, the nuclear force and the nuclear reactions are going inside or inward, not outward. Okay, because strong nuclear force and strong and bigger nuclear reactions or high nuclear reactions, something like that. Okay, but the thing is they have to react with each other during the radioactivity process or during the chemical reaction, just three particles. Okay, something like that. Okay, so don't confuse with the mass number and the mass. Really, the mass meaning there's a figure in, let's say, in kilogram, then you can convert that to the pound, to the gram by using the conversion factor. But the mass number will be having no unit, it's only number. Okay, only number. Okay, but don't forget this one, the number of electrons is always equal to the number of protons regardless to the sign, whether it is negative or positive. Okay, that's why we don't put sign here. Okay, so proton 1, okay, like as an electron 1, okay, and the neutron is 0. So the number of electrons is equal to the number of proton. Okay, not the neutron, because the neutron is always 0, the mass number. Okay, and it doesn't matter whether mass number or charge of a neutron is always 0. Okay, So remember this. Okay. So this will be the end of our atomic theory, or the three particles of an atom, you know, the behavior in the nucleus, or as a atomic theory as a whole. Okay, something like that. So these concepts will be used in the nuclear reactions later, that I will be discussing also for the nuclear chemistry. But take note, this is also the basis for the topic for electrochemistry and electrolysis. Okay, so I need to add one more constant for the basic unit of an electric charge, which is 1.6020 times 10 to the negative 19 coulomb. This one is very important, huh? In the electricity concept, in electrolysis and in electrochemistry. So the basic unit of an electric charge is 1.6020 times 10 to the negative 19 coulomb. Or if the question will say like this, what is the unit of an electric charge? Your answer will be coulomb. Okay, because it does not require really the specific uh, number or the specific value. Again, if the question will say like this, what is the basic unit of an electric charge? Your answer will be only coulomb. But if the question will say, what is the value of an electric charge? Okay, your answer will be 1.6020 times 10 to the negative 19 coulomb. It should be perfectly stated. But if the question is, what is the unit or the basic unit of an electric charge? Your answer will be coulomb only. But you will put the figure if the question will say, what is the value of the electric charge, like that, okay? Or what is the unit of an electric charge, so like that, okay? You have to put the specific value. Usually, based on my experience, always asking for the what is the unit or what is the basic unit of an electric charge, you have to put coulomb, because nobody dares to memorize the exact value for that. But if you memorize that better, the 1.6020 times 10 to negative 19, like that, okay? Just like the Avogadro's number, like that, you have to memorize it specifically, then it's perfect. Meaning it is more advantageous for you to memorize the exact unit and the exact value or the exact number for that particular, topic or subject we are referring to, something like that. Okay, thank you so much for listening. Okay, I will end now my live streaming, and if you are not subscribing yet my channel, then you can subscribe. You can click if there is any notification bell in my videos, if have. Okay, and then you can comment in the comment section, of course. You can like, okay, like that. And please do not escape the ads and the videos in my YT channel. Okay, so it doesn't matter how long you will view, as long as you will take a look, even though 0.001 second. Okay, so thank you so much for everybody. Okay, thank you so much. This is again, I'm Singer Eternal Voice. God bless. Bye bye, everybody. Okay, see you later.